Welcome back. As a continuation to our previous lecture, we are going to discuss few more problems in this lecture to check whether the given sequence or series is uniform convergent or not. Okay, this is our third example. We are about to show that the sequence Fn, where Fn of x is defined as 1 upon x plus n, is uniformly convergent in any interval 0, b, where this b is positive, real. Okay, now here if we identify the limit of the pointwise limit of this sequence, what do we have? It is limit n approaches infinity 1 upon x plus n. This is 0 irrespective of what x we choose in the interval 0, b. Okay, that is Fn of x converges pointwise to 0. Okay, now let us check whether this pointwise limit is our uniform limit of convergence. For any epsilon positive, we would like to have Fn of x minus f of x is less than epsilon. Okay, what is this absolute of Fn of x minus f of x? It is absolute of 1 upon x plus n minus 0, which is nothing but 1 upon x plus n. We expect this to be less than epsilon, right? Okay, this is gonna happen if x plus n is greater than 1 upon epsilon, that is n is greater than 1 minus epsilon minus x. Okay, we are able to see that this 1 upon epsilon minus x decreases as x ranges from 0 to b. Okay, and thus the maximum value is 1 upon epsilon, that is supremum of 1 upon epsilon minus x is nothing but 1 upon epsilon only. Therefore, absolute of Fn of x minus f of x is less than epsilon for n bigger than 1 upon epsilon. So you can identify some n which is greater than or equals this 1 upon epsilon to be or big N, then your requirement is satisfied. Thus we conclude Fn of x converges uniformly on the closed interval 0, b. Okay, the next example that we are going to see is, now we will have to show that the series summation Fn where Sn of x, that is sum of first n terms, is nx e to the power minus nx square. The series is a pointwise and not uniform convergent on any interval 0, k, where this k is any positive real value. Okay. First of all, we shall find out the pointwise limit. What is the pointwise limit? That is summation n runs from 1 to infinity fn, which is nothing but limit n approaches infinity partial sum. Okay, Sn of x. So this is nothing but limit n approaches infinity nx e to the power minus nx square. Here we are letting n go to infinity. So this exponential term will make us go to 0, whereas this product nx term will make us go to infinity. So what would be the result in this case? If we observe, nx would be very much bigger than e to the power minus nx square for large n. So this exponential term will go to 0 very faster than nx going to infinity. So this limit is 0. So we have a pointwise limit that is 0. Thus the series converges pointwise to 0. Now suppose summation fn equals f uniformly, that is, this convergence is uniform. This is what we assume on 0 comma k. If that is the case, then for any epsilon positive there exists an integer n such that for all x greater than or equal 0, absolute of Sn of x minus S of x equals nx e to the power minus nx square would be less than epsilon for all n bigger than or equals n. Now let me fix n naught to be some n. Okay, I am choosing n naught be any natural number such that n naught is bigger than this n. Let's choose an n, as well as this n naught is bigger than e square epsilon square. Okay, then I am choosing x to be 1 upon under root n naught. This will fall in this interval 0 comma k only, right? And I am choosing my n to be n naught itself. Then from 1, what are we having? So absolute of Sn. Okay, so let me just directly calculate this quantity. Nx e to the power minus nx square would be, n is what? It is big n naught. X is what? 1 upon under root n naught. Okay, and this is e to the power minus n naught into 1 upon under root n naught the whole square. So which is simply under root n naught exponential of minus 1. Right? It is just that under root n naught upon epsilon, under root n naught upon e, which is less than epsilon from 1. Okay, this tells us that under root n naught is less than epsilon into e, therefore n naught is less than epsilon square e square, but we have chosen n naught to be greater than e square epsilon square. Okay, so which is a contradiction. Thus summation fn does not converge uniformly. Okay, so still now we have worked out problems based on the definition of a uniform convergence. Okay, now we shall work out few problems based on the other theorems that we have discussed. That is, we will find out. Okay, first let me give you the problem and then let me recall the theorem that we are going to use. Okay, now we are going to show that the sequence fn of x, that is nx upon 1 plus n square x square is not uniformly convergent on any interval containing 0. So this is the problem that we have now. Okay, here the result that we are going to use is, suppose if limit n approaches to infinity, fn of x is f of x pointwise, and we will let mn to be supremum of the difference between this fn of x minus f of x over the given interval. Okay, thus convergence fn to f is uniform if and only if mn converges to 0. Okay, this is the result that we will make use here. Here, what is the pointwise limit to this fn? Limit n approaches infinity, fn of x is going to be 0. Okay, this we have checked for all x. Okay, now what we have to do? What is our mn? It is supremum of x belong to a comma b. Okay, it is nx upon 1 plus n square x square minus 0. And this would be equal to what? So now we will have to find out the supremum of this value. So whatever value we substitute, be it anything, and if we just see what is happening, okay, we are concluding that it would be 1 upon 2 if, okay, the supremum is 1 upon 2 at x equals 1 upon n. At this point this will happen, because if you directly substitute x equals 1 upon 2, you will have x equals 1 upon n. So in the numerator you will have 1, in the denominator you will have 1 plus 1, that will be 2. If you substitute any other value of x which involves n or doesn't involve n, that doesn't matter, you would be able to get some value which is smaller than this quantity. Or there is another way to find out the supremum. So supremum over some finite interval, this is what we are talking, right? So it is just that finding the maxima. If you consider this function nx upon 1 plus n square x square as some function of x, then find its derivative and equate it to 0 to get some value of x. Okay, since we are in the closed interval, evaluate your function at, suppose whatever the value that we are getting, if we call that as x naught, let us have it. So find what is g of a, g of x naught and g of b, whichever is the largest, that is your supremum value. Okay, this way also we can find. If x is given 1 upon n, then that will give us the supremum value, that would be 1 upon 2. Note that this 1 upon n goes to 0 as n approaches infinity, and hence mn doesn't go to 0 if this 1 upon n is a member of this interval AB. That is, if 0 is in the interval AB, then the sequence does not converge uniformly. Okay, we will look into one more problem. Fn of x is given to be x upon 1 plus nx square, and x can be any real value. We will have to check whether it converges uniformly or not. First of all, what is the pointwise limit to this function? The pointwise limit is 0. And Mn is what? That is, okay. So first of all, let me calculate what is Fn of x minus f of x, which is simply x upon 1 plus nx square, absolute of this quantity. And Mn is supremum of this quantity, right? Okay, here the same ideology, if you want, we can implement it. It is x upon 1 plus nx square. When we differentiate it, it is v u prime minus u v prime, that would be 2nx upon 1 plus nx square the whole square. So this would be 1 plus nx square minus 2nx square upon 1 plus nx square the whole square. When we equate it to 0, what do we have? We will have 1 minus nx square is 0. This implies nx square is 1, therefore x is 1 upon under root n. So you will have two different values of x, right? That is 1 upon under root n or minus 1 upon under root n. Okay, whatever it is, if we just substitute this value into this function, what are we going to have? So g of 1 upon under root n would be 1 upon under root n plus 1 upon n times of 1 upon n, which would be simply 1 upon under 2 times of under root n. And g of this is minus 1 upon under root n, 1 plus n times of 1 upon n, so it is minus 1 upon 2 under root n. In either cases, our Mn would be 1 upon 2 times of under root n, right? And this go to 0 as n approaches to infinity. Thus, our Fn converges to 0 uniformly, right? So with which we will conclude this lecture, and in the upcoming lecture we will work out few more problems and discuss few more results on uniform convergence. Thank you.